Hello and welcome to lecture 2A. This lecture is extension of lecture 2. Before going to explore more and more about the surface engineering, corrosion and degradation because of that, it's always better to look at the commercial perspective. In other words, if I say the commercial perspective, we need to have a number of questions, something like that. Does surface degradation mean deviation of actual surface from ideal surface? In my view, in my way, I can say that in general ideal surface means smoother surface having a round edge, smoother transition to minimize the crack initiation and features which are susceptible to the corrosion. So, we want something like ideal surface. That is what we say, that if the surface is not ideal, to some extent it is going to go as with a surface degradation. Next question comes in our mind, will there be any noticeable changes to product's ability to perform? In my view, or maybe as per my knowledge, friction and wear have a severe economic implication, and expenditures related to replacement, maintenance, productivity are huge. Another thing is comes when we go ahead with the condition monitoring, we say the requirement of monitoring system and qualified workers who can understand, have a good knowledge about this system or maybe the science, they are very costly. So, if we at the beginning itself we take all the decision what are we going to do and then whether it will be cost economic or not, then it will be always better and better. As far as my knowledge is concerned, in the most of industries like automotive, aerospace, electronic, surface degradation plays very important role to uphold the product quality requirement. And if you want to increase the productivity, improve quality or safety, surface degradation consideration is very important. Sometimes people say we do not want a perfect surface, we do not want ideal surface. Yeah, those are possibilities are there, because we can create surface irregularities on a surface to improve the performance, but we will discuss those points in a separate lecture when we think about or when we discuss about the design of the surfaces. For time being, we say the surface degradation is a bad, and then if it is away from ideal surface, then we need to look at the economics, we need to look at the what are the penalties which will be paid because of the surface degradation. So, start with this, I have used the word here in the slide, analysis of surface degradation. Question comes, how do I analyze? We have heard about the failure analysis, but here we are just concentrating only on surface degradation. First question again will come something like what are the primary causes of the surface degradation? Is it a design? Is it the materials or manufacturing processes? Maintenance strategies, because every system will degrade over the time. So, what kind of maintenance, how we are trying to maintain those systems will be important. How will there be any environmental issues? Sometimes temperature increases, humidity increases, corrosive environment comes, pollution increases, will that be a major reason for surface degradation? So, what we really need to look at, whether the design fault, material fault, manufacturing fault, maintenance fault or environmental casualty or maybe the reasons the changing environment is happening. So, we need to look at all those factors. Now, how do I really identify surface as degraded? So, we have a number of methods. We say the visual examination is a easier one, but we can't see lesser than 50 micron. So, we will not be able to see the initiation of the fault. For that purpose, we can go ahead with the destructive and non-destructive testing. We can go ahead with a number of experiments in the laboratory, collect the data, necessary data, process those data and do interpretation of those data. So, these two things are very important. What are the causes and how do we analyze it? For that purpose, we require a logical, systematic approach to find out causes of surface degradation. Then, if we know the causes, we need to take necessary steps to reduce the chances of degradation in the future. Why I am just saying this one, many times we develop a new process, many times we develop a new product. Initially, we will not have a complete knowledge. So, system may fail also because of that, and then we need to have a closed feedback system to understand the failure reasons and continuously rectify. So, it is not the day one we will be able to launch a product. Maybe it has to go through the number of experiments within the lab, within the premises where it has been developed, and analyze all those, and when the almost foolproof, then only the launch the product. That's the way we maybe most of the industry are working, and that's why we are emphasizing on that. We should have a logical and systematic approach to understand each and everything about the surface, how do we mitigate it, and whether it will be cost economic or not. Many times we may say that we don't want to lose $100 to get a $1. That should not happen. So, we really require cost economic analysis from that point of view. What is the systematic approach? If you go through the ASM handbook volume 11, they provide one fishbone diagram. They say this is a cost effective diagram, which is very good. You need to look at what are the operation, whether is there any overload, or is there any installation error. Look at the design aspect. Design aspects includes the material selection, kind of the shape, configuration which we have given. Sometimes we also look at the manpower. Human people, the person who is involved in this kind of operating system, whether he is skilled enough or whether he has a complete knowledge about the system. Maintenance strategies, then what is the strategy we are opting for maintenance? Is a regular maintenance, once in a while maintenance, or maybe that we have some sort of sensor based maintenance. And most of the time it says that because of the loose connections, and I have observed particularly nut and bolt connections, they become little loose, maintenance problems start on the mounting big way. So, that's not correct. So, we need to have some sort of a strategy, some sort of and then write up for the even operating person, that this is what we need to follow. And wherever we do not have this kind of documents, wherever the knowledge is lacking, most of the failure happens because of that. So, that is important. Again say design is the one aspect, but manufacturing I can do very good design, but if I am not able to manufacture well, I am not able to quantify well those manufacturing defects, then there will be problem. So, that is why I say what are the defects, and sometimes the defect will come again like in a heat treatment process. So, these are the major items. So, whatever processes we are adopting or opting, maybe new process, but if we do not have a complete understanding, or operator does not have a complete understanding, the failure will be there. And if you club these the arrows, then we will come up with some sort of failure mode. So, this is about a fishbone diagram. Now, if I try to explain fishbone diagram in my words, what I will say, the fishbone diagram sometimes we call as a cause and effect diagram, sometimes we say Ishikawa diagram, is basically visual tool. We are able to see that for identifying and analyzing the various source of problems and issues. It is a kind of the brainstorming method. We used to start thinking about in a liberal way what will be the what are the possibilities. So, I can say it is a kind of brainstorming method to find a plausible reasons and factor contributing to the problem. Now, why the fishbone, the name comes, is that this diagram is shaped like a fish skeleton with the problem and effect represented at the fish head, and various reasons, various causes are the fish bones that branch from a main backbone. Each branch is related to certain category, as we use the word the manpower, method, machine, material, measurement, and mother nature category. Sometimes people say it is a 6M diagram. Manpower is a number 1, method, machine, material, measurement, and mother nature category. That is why we are using, sometimes people say the 6M diagram. Now, when we talk about the manpower, what we intend to say is a manpower resource include a factor like skills, training, and knowledge. Do we have all this? Whether a person can operate effectively, do we have some sort of automation system, or some people are well trained about those? Do we have sufficient knowledge to rectify the whatever the problem comes at that is a micro level or maybe very small level. Now, when we say the process and procedure used to followed in a system can be referred as a method, that is a second M. Comes to the machine, we say process equipment like tools, technologies which we are using can be named as a machine. Materials is something like raw material, commodities or resources which have been utilized for the complete machine or maybe the system or subsystem or the components can be named as a materials. We also required a quantification, that is why we use the word measurement or metric, and we also add sometimes statistics, because when we come to the industry, statistics play a very important role. When we scale up the number of systems, naturally statistics plays a very important role, because even the 1% and then the failure will cause a major failure, or maybe the defame the complete company. So, that is why we require statistics also to judge the performance and quality. And as we say that we are in an environment, so mother nature environment means what are the external elements, what will be the humidity, what will be the temperature, whether there will be rain, there will be some sort of pollution, that will be the playing important role. So, once we have all this knowledge, we can make a fishbone diagram, and then we can start analyzing, we can brainstorm, so come to the some conclusions based on that. Now, I will just take one of the example like a mechanical failure. I say final failure is a mechanical failure. So, fishbone the head is a mechanical failure. Then what we are mentioning in that, when a system, process or component fails to perform as expected. Now, again many times people feel the failure means breakage. Oh, one piece should be divided and the cracked into the 5 pieces, 10 pieces or 15 pieces, not that way. We say if the component is not able to perform as expected, what was supposed to be done, like I want some efficiency 98%, now my system is giving 95% efficiency, for me the system has failed, right. So, this is what my laptop is not able to perform like i9 or i7, it is working like i5, i3, so system is failed. So, actually the failure is different, but the whatever intended function, whatever we were expecting from a component, subsystem or system, it is not performing that much, that means there is a failure. So, that is what we are saying, that is its system has failed. Now, when we, because we are discussing about the mechanical failure, I say the mechanical failure might take a form of a structural collapse, that is why there may be the breaking or maybe the bending or something like that. Another one I say the non-functional machinery, machines are not operating. Last one, very minor one, we say the worn out parts. Part is maybe the whole machine is there, working condition, but with the few parts are not performing well. So, that will be also turned out to be like mechanical failure. So, what we really require a root cause failure. What is the root cause of the failure? Now, it can be say the various faults, maybe the system has a various fault, because we do not want a complete failure, we want to see the initiation of the failure itself. So, the big loss to the company should not happen. We should be able to capture the beginning itself, so that we can correct it or rectify it immediately. So, what we say that maybe some sort of faults can be crack, can be fatigue, can be creep. This is a mechanism, we will show the microstructure in our later lectures, or it may be corrosion also. Another important thing is that many times we use the word root cause failure, and then if you look at the third stage or fourth stage, failure may look like a singly occurring because of the bending or because of the fatigue or because of the high temperature possible, but often it comes in a simultaneously. So, the failures may occur or failure mode come in a tandem order. So, that is also we need to really keep in that in a mind. And how do we really check the mechanical the failures? Complete fracture analysis will be there, fractography will be explaining in a later lecture. But what is the easiest one, or maybe at the beginning itself, we say better we look at the wear debris. If there is a mechanical system, there will be some sort of debris will be coming out of the system. Can we do analysis of the wear debris? So, what is wear debris? It can take some sort of chips, it can take some sort of flakes, it can be particles, or even the nano sized dust, which is not visible to us, but we have some sort of setups available which can be diagnosed, which can really determine the diagnosis of the fault of failure. That will be the very important for us. So, that is the reason why we are saying that to guarantee system and process dependability, it is essential to identify failure modes. And of course, if you are able to find out the initial crack, fatigue or whatever the corrosion initiation, that will be the far better, and we can immediately find out the reasons, and then we give us some sort of effect also, or maybe say essential why it is happening and how do we correct it and then mitigate it. It will be important. So, fishbone diagram sometimes is very important, However, there are a number of other methods also available which can be utilized to mitigate the failures and to brainstorm the various causes of the failure and then identify the failure. So, various techniques are available, we will be detailing those things in later lectures. But it is essential for us to understand, to have a complete knowledge. For that purpose, this kind of course is very important, and we need to really rigorously do all those things to save the cost, to save to make it overall economic or not. So, how whether economic or not, or whatever I am going to suggest, we need to really take a decision on that. So, I will try to provide you sufficient knowledge so that you can take a decision, and then sometime it is in one situation it is favorable, another situation may not be favorable. If we have a knowledge, we can take those important decisions. Now, let us take a couple of examples. I am just taking first example from my lab. We have a gear setup where there is some sort of a dynamometer to load the gearbox, motor to drive the gearbox, and there is a small gearbox over here which is a single stage spur gear, and the details of spur gears are given here. We have pinion with having number of teeth 27, gear having 53 teeth, pressure angle is same 20 degree. We have kept lower hardness 30 plus minus 2. Of course, we can keep 60 to reduce the wear, but we want to see the wear, and apply load, or maybe apply torque is a 14 Newton meter, and we operated this setup for the 198 hours to see what is really happening on here. Now, if I see what is the overall operation, in this case is a gear operation. Now, we really go have the regular maintenance. What is the meaning of that? We keep collecting the oil sample. Now, oil sample can be collected after 10 hours, 20 hours, 30 hours, depends on our strategy how we want to do analysis that way. Now, when we do collect the oil sample and filter it, we will get a wear debris, and then we need to analyze those wear debris. You can see this is a 10 micron, the bigger particle. This is also the kind of the plate formation with some sort of edge also. This is a very small particle size, and this is another one flak size, the bigger size dimension. So, these are the important we can use a SEM to look at to see the details of this. And the 100 micron I am able to show the surface also. So, it is interesting. You can see the debris which I get from oil, and the surface also has this debris. So, debris does not come immediately out of the surface. When you try to analyze it, quite possible some debris will remain stick to the surface, maybe because of addition, because of the abrasion embedment happens, or maybe still in the process of the wear out, is in the process of the damage. So, you can see here the surface degradation is related to the here. We are able to see the debris, we are able to magnify the surface and able to see that yes, there are number of particles on that. So, that is why I say the wear analysis through oil, and then we can do a classification also. We can say there is a cutting wear, very long fiber, and then long wear, then the particle something like dimension in one direction, dimension is smaller one, maybe the D1 here, and this is a D2. And then this ratio is very big, like a D2 by D1 is very large, then we can say this is a kind of cutting wear. And then the plate forms comes as a sliding wear is indicated when we have a spherical particle, mostly the fatigue or maybe some sort of rolling motion is happening. So, we can really judge whether the surface is degrading or not. So, this is a way we can really judge and then without opening a surface also. If we do not want to open a surface, maybe the gear surface itself, we do not want to see that, then we keep collecting the oil sample, we can find out the debris, maybe the debris 1, debris 2 and debris 3. Now, depends on the concentration of debris, we can decide what kind of failure is going to dominate, which will be the main cause of the failure. So, if I try to express it in other words, we say that what we have explained is something like a wear debris. And when you collect the wear debris, you need to do image or image analysis, then the particles which are coming out of the surface, and what is the really relation of this relation of the particle which has been getting removed from a surface with a wear surface, and how it will really affect the gearbox performance. Maybe in short span, maybe say when the wear starts, it may not be visible, it may not be able to noticeable by some other method, but all analysis of this debris analysis may reveal those kind of faults. We can take immediate actions on that. Another one thing is that to investigate the surface degradation of gear, it is important to define the complete tribological system. Maybe tribological system is something like when we have a gears, we may have a bearings also, may have a seals also. So, complete tribological system is important to define. Then we need to figure out what will be the oil sample and then the frequency, how many times we will be sampling the oil in a 24 hours or maybe 10 hours or 5 hours. That depends on the kind of the concentration of the wear debris which we are getting and then that point. Another one is that once we get the wear debris, or we filter out and maybe say they remove the oil from wear debris, and then we can go ahead with a microscopy or a spectroscopy or a laminar analysis. Then we can judge what will be the what kind of the wear debris particles we are getting, what kind of the failures will be there, what kind of remedies can be there. So, these are all interconnected. Another thing we say that if investigation comes from the existing particle with a spherical, lamellar, or maybe say the irregular shape of the size, but if size is a more than 10 micron, then it is a bit alarming. If a lesser than 10 micron, we know that will happen, because when the two surfaces come in a contact, they will wear with each other and then wear each other. Maybe the particle size is much smaller, that will not really matter much. Quite possible what we say the compatibility, maybe the two surfaces are trying to make surfaces smoother, and so that then that can go for the longer term, or maybe say performance will be improved. And sometime we say that this is a part of the bathtub curve, which we have already studied in previous lecture. So, this is what we need to think about. However, if the particle size goes more than 10 micron, which is a worrisome, if particle size goes beyond 100 micron, then we say, oh, there is something wrong, and then we need to take immediate actions. So, 10 micron to 100 micron depends on the number of particles. If number of particles are not many, then again we may have some sort of thinking that there will take little longer time. Surface degradation is not that phenomenal, and maybe the occasionally few particles we are getting. So, it is not a one particle you get and immediately if you know some surface is getting damaged. It is once in a while we will be getting those kind of things. Now, look at this, maybe we will try to cover another example. We found the one reference in 2006, and then what they have done, they have made a very small setup. You are able to see the complete setup here, and there is again a gearbox, which we also covered in the previous slide, was a gearbox. And then how to collect the sample also have been defined in this manner. So, what they did in this case, they develop a one experimental setup to test medium carbon steel. We can use a different kind of steel here, where they have used a medium carbon steels, particularly which is required for the centrifugal pump. Now, this circle diameter for the input gear is something like a 40 mm, module they kept 20-degree pressure angle. In our previous slide also we covered and maintain the 20-degree pressure angle, which is much more common compared to 14.5 and 22.5, while PCD of the output gear is a 30 mm. So, naturally we can say the gear ratio is 4:3, that means input is a 4 and the output is a 3, when we say 3/4 if we look at from output point of view. The face width of both the gears, they have maintained 8 mm, almost same, so that the loads of maybe transmission is not that kind of problem. However, they kept the driver in the gear a higher hardness 179 handle in the B scale, or the scale compared to the driven, which is a 170. So, there is a minute variation in the hardness of the gears, which will not impact that much. Now, they use a different kind of oils also in this case, and then what they collected something like a they accelerated, basically they operated at the normal condition, they operated overload condition, and they operated also cyclic load. So, this is basically they are changing the operating condition, that continuously load is increased and the frequency is increased. Now, operating duration is a bit different, has been mentioned here. This is the what I was mentioning of the overloading, or the loading is continuously increasing, that has been mentioned here. In addition, they continuously increase the speed also. So, this speed increase is also really, we are trying to accelerate the wear rate to find out what is really happening in this case. So, that has been done. Now, when there is a oil and then we keep collecting the oil sample, this has been mentioned, our collection of the oil sample, what we do, we try to filter it, and that is why they have used the filtergram method to collect the this debris on a microscopic slides. Now, they found very high concentration of air debris, which indicated that when they are trying to accelerate the load condition, try to accelerate the speed condition, they are finding a lot of particles or a high concentration of air particles. Now, they observe under microscope, again this is a microscope, we are not gone to the SCM. So, that smaller particles we are not talking, we are talking bigger particle. You can see the big particle, one here, particle here. However, there are small particles also here, and then there is another big particle. So, the big particles are also there, but small particles are also there. Now, what they from this figure, what they could conclude, that there is no not existence of the many fatigue particle, only few particles are having the fatigue features. So, in the they concluded no fatigue failure, even though the cyclic loading they do not find the fatigue failure is dominating there. However, they operated this completely only for the 70 hours. It is not that they have operated for 200 hours, what previous slide I showed is about 98 hours, while in this case they operated the 70 hours. Another one, they found a number of particles which indicates a severe sliding speed, and then however, they found only few particles which are more than 100 microns. When the particles are only few more than 100 micron, that means still the surface degradation and in the earlier stage or initial stages. If we take away these, we can really minimize the surface degradation. However, they did all this under the overload condition and high speed condition, and what they finally found, this is the initial surface that the photograph has been shared. While they are able to see the tip, that there is a lot of sliding on a gear teeth, they are able to see the gear teeth sliding, and we are able to see the pitting of also the gear teeth. Now, even though they say there is no fatigue failure, and pitting mostly happens because of fatigue failure, that means the surface the sliding wear is causing a more problem than the overall effective and then the gear tooth, which is the area available to the sustain that this load is continuously decreasing, and then only the pitting will start. So, root cause in this case will turn out to be sliding wear, not a pitting wear as such. That is what they concluded. Of course, they are able to observe both the things, but say sliding wear dominates compared to the pitting wear in this case. Let us take a third example. I am just trying to provide more and more examples, so that I can give a complete understanding about the surface degradation identification, how do we diagnose, and maybe take a judgment based on that, and what kind of a new method also can be developed to do this kind of testing or surface degradation testing. So, what they have done in this case, third one, which has been again we have taken from a reference which was published in 2007. We say in this case they are using one stationary disc. So, this disc is a stationary, ball is rotating in and then the track has been shown over here. They try to keep this in the ball is 5200 stick, very high hardness in this case is 50 HRC, while 8 mm is the diameter of the ball. While desk they kept a soft surface relatively, the 4340 steel is a medium carbon steel, hardness also is a smaller compared to maybe 1/3 compared to the ball, diameter is a bigger, thickness is the same, thickness is kept in this case is the same, also thickness is 8 mm, while ball diameter is 8 mm also. In this case they also observe the surface roughness. Surface roughness is the first time in this case the 3 example I am covering, because surface roughness plays an important role. In the beginning of this lecture I mentioned that what is the meaning of surface degradation? Is it some deviation from ideal surface? Yeah, if the surface roughness continuously varies, increases, then we need to think, yeah, something is wrong. However, we will be adding few more terminology here in this slide, and then this all experiments were done at the temperature 20 degree, and then relative humidity was kept around 30 to 40%, not very high humidity, because when we go for high humidity, then there is a chances of corrosion also will be there, and then we need to count those things. So, complete they perform experiments with the 2 oil SAE40 and N32. You can see here the density difference is not that significant, however, viscosity difference is significant. We can say SAE40 is a thick oil, and N32 in this case is a thin oil, and this viscosity also is almost 3 times more at 100 degrees centigrade. However, it is much more stable. We say that in this case N32 will not deteriorate that much as deterioration happens into the Si40 with increase in the temperature. Flash point is also been mentioned, that means we cannot operate, and of course we are operating at the 20 degree. So, flash point does not make much sense for this purpose. However, for completeness it has been given, and even the pour point or flow point has been mentioned also in this case. Now, coming to the real experiments when they conducted. So, what they did, this contact area, whether this area, the track which has been shown here, this has been soaked in the lubricant. Now, as I mentioned, there are two different lubricant. In one case Si40 and another one 32, and then each experiment they conducted twice, because when we do the laboratory test, and these are the statistical, we need to conduct more number of times. It should not happen in one time I am getting good results, and second time also I will be getting good results. So, we require more and more number of experiment to be conducted, and we should satisfy that statistically. Yeah, in this case they have done twice, but few people do experiment up to 5 times also, that they are able to conclude the results in right manner. Now, what they mention, the test 1 and 2, test 1 is with the lubricant 1 and the test 2 is with the lubricant 2. In this case they experimented, and then because of the high viscosity they found the severe wear occurs only after 168 hours, while in a thinner oil N32 the severe wear occurs after 72 hours. That is what they have done. Now, what is the interesting thing? Earlier first two cases we observed, we were observing the gear pair, or maybe say gear teeth, while these people did something like a wear debris particle analysis. They collected around 20 particles in each case, and they figure out what will be the average surface roughness, what will be skewness, what will be the kurtosis value of those particles. So, here they are not judging the surface, they are judging the particles which have come out of the surface. Maybe say, and then the surface has been damaged and the particle have come out of that. So, that is what they were trying to analyze, and then what they found in test 1 and 2 SA value is more or less same, while skewness value in this case in test 1 was on the severe side, on the positive side -27, while in test 2 it is a very low slightly negative, maybe almost negligible negativity in this case. However, the kurtosis value also in this case is 2.53, 2.34. What is the meaning of this? When we talk about skewness, when we talk about the kurtosis, naturally we need to talk something like what is the really interpretation of these values, why we are calculating, and what will come out of that. So, let me say in slightly different manner. We say that in we are talking about the 3 statistical parameters. So, average roughness, skewness and kurtosis all are the statistical parameter. We do not take only one measurement, we take many measurement and then we analyze statistically. Now, some researcher, what I understand, that they suggest that skewness and kurtosis value are sufficient to give indication that whether machine is going to fail or not. So, these are the two parameters, that is why we have been referring skewness and kurtosis. These two parameters are related to the surface and then they are statistical parameters. So, that is why they have much more value, what we are mentioning. Now, in this case we can find out the skewness and kurtosis for almost all the machine, even the gearbox, and that is why we can operate and we can find out this value for the gearbox also. In gearbox, in normal condition, in abnormal condition, we can compare, we can do a kind of the trend analysis to come up with the results. Now, what is the really kurtosis? We say the kurtosis describe how smooth or jagged the surface is. Its value, if it is a value is low, then we say the machine is normally operating, it is operating well, not much problem. But the value increases, then what something is there, we say the rotating part is malfunctioning or it is not really properly functioning. So, in other words, higher value of the kurtosis means there is more chances of the surface peaks. If the surface peaks are increasing, naturally the surface is getting rougher and rougher, and then it is a very alarming, and we need to see that maybe surface degradation has started. So, this is a, I am using the word easier one to find out and dig out the information whether the surface is degrading or not. So, the kurtosis plays a very important role from that point of view. Now, second term which we use is skewness. What is the meaning of skewness? It says that how much the data point deviate from the mean value. So, we are comparing with the mean value. Now, positive skewness, generally we say we should go have the positive thinking, a positive this and positive that, but in a skewness we say positive skewness means something wrong, uneven distribution, it has a tail upward side, and then a positive value means machine is likely to be defective. So, here the positive skewness is not required, we should have either 0 value or should have a negative value, then it makes much more sense. If it goes on a positive side, then something is wrong. Now, that is why we showed the previous slide also the lecture, and then this skewness increases positive side, and maybe a possibility of the more value. Now, another one thing is interesting, because if somebody says, oh, skewness is more than sufficient, I will only measure skewness. No, if you look at the normal Gaussian distribution, skewness is 0, that is where the mean value we find out. However, kurtosis value is a 3, that means kurtosis 3 or lesser than 3 may not be that problem, but more than that, then will be problem only, right. And that is why we say for completeness we require these 2 parameters, and then the easier one also we will add few more parameters to give a better judgment, better results as such. Now, one good thing about this statistical parameter and measurement is that in recent days we have learned the machine learning algorithms or artificial intelligence. Now, this can be clubbed together. We say that recent advances in machine learning algorithm, we can conclude that from a surface feature itself, by measuring the skewness, kurtosis, root mean square value, or maybe average roughness, will be sufficient to draw conclusion whether surface degradation is happening or not. So, it is very good for us that even the measures are easy to are cost economic to find out what is really happening to the surface, and if we know the kurtosis value, skewness value, then we can judge whether surface is going to get degraded more and more, or maybe then they are going for refinement. So, both the values are important. Of course, I mentioned also that RMS value, that is the root mean square value, is also important. Some roughness value, which is generally the most from the manufacturer quoted. So, we need to relate on the average roughness with the RMS, kurtosis and skewness. Those will be important for us. Now, I talked many things about the surface roughness or maybe the skewness and the kurtosis. I am just trying to show the profile, and I have picked up this profile from my book. You can see here I published one book in 2016, and then that say the fundamental of engineering tribology with application, and I picked up this figure 8.9 and 8.10. Is from the book itself, as it is I am maintaining the same figure number. Now, what has been shown, figure A, B, C, D, in this case we are saying this is a positive skewness, and that is why we say we should not go with the positive skewness, we should be avoiding. While and then this skewness is a negative, is okay for that. Sometime we require some sort of extra lubricant, increase in the contact area, we go with a designing of the surface with a negative skewness. However, in mostly for Gaussian distribution it will be the 0. Most of the surfaces should have a 0 value of the skewness, we should have a symmetry and then about the mean value. Now, coming to the kurtosis, we say that mostly the kurtosis surfaces are lesser than 3, and that is why the two slides and the previous slides we have shown as lesser than the 3 kurtosis value, and I am saying that even the RSK and for Gaussian distribution, this the kurtosis value can be 3. Well, if you look at this is a more than 3, and this is what we say we do not want this kind of surface. So, either we have this surface or we have this surface, or combination, we say that this surface is something is wrong, some sort of deterioration or damage of the surface is happening, we should take appropriate measures. Now, and then this is what we have mentioned about some sort of the product and then some sort of a surface roughness feature. Now, how do we go ahead when we say the mitigation or maybe the economic analysis, and when do we take what decision? So, for that purpose I recommend the feedback loop system, which is feedback of surface degradation and product evaluation should happen simultaneously. Now, What is the meaning of that? We say that every system or subsystem or component is meant for the doing some function. For that purpose, we require the design features, we require a material selection, we require a manufacturing, we require installation, and we require the services. It can be like the maintenance services also. Now, we continuously keep checking, or maybe we follow this path, and then we end up that find out whether is there any surface degradation or no. Now, if there is a no surface degradation, we do not have to go to the economic side, we do not have to go to the safety side. But if there is a surface degradation, then we say, oh, so function is failed, or maybe say we have judged the function is failed. We look at the safety and then we look at the economics. If it is not failing, we should go ahead with the feedback. Now, feedback, if we know that design is perfect, no problem, and then if there is a design is perfect, but material is failing something or some sort of a symbol we are getting, then we should go ahead with the feedback to system, or we can go ahead with the manufacturing, or we go for the installation. So, every stage we can have a feedback system. So, it is not that only the design is feedback. We can judge maybe the material is wrong, then we go ahead with the feedback system. Now, this is not for complete product development, the product which has been developed. It is basically when we are developing the product. So, that is in house we do performance test and then we continuously modify it. That is why I say that we do not launch a product immediately, we develop a product, it is showing the function, but we should have a perfectness in the design, we should have perfectness in the material selection, we should have perfectness in the manufacturing, perfectness in installation, and all the service related parameters also we should have a completeness. And wherever we find a minor faults, we should go back to the corresponding discipline or the keywords, and we modify it. So, that is why we say the utilizing insight from analysis of surface degradation, we will be continuously finding the surface degradation. Quite possible initial surface degradation will not cause a complete failure, it will still be showing a functions. So, if I say that my performance should be 95% to 100%, right, and then I am getting 99% or 98%, 97%, quite possible I figure out I want to go jump from 97 to 99%, what corrections need to be done. So, that is what we need to go back to the feedback system. So, that is why I say utilizing insight from analysis of surface degradation, feedback loop comprises adjusting and enhancing the product design. Okay, and the product design, or product manufacturing or product installation or product services. So, we need to continuously give a evolution to the product, or product evolves with our analysis. So, that is why the surface degradation or the analysis of surface degradation is very important. Now, once we complete all this, then again comes a test. So, we need to perform the test also. Quite possible initially we are doing this kind of test, but without performing test, then we need to really make a product and continuously do the testing, and then again we need to have observe also all the failures or all the faults which are getting coming to the system. We need to continuously do a testing and validate, and then whatever the correction, suppose I change a material, I change a material shape, or maybe the sizing, then we need to really check whether it is performing well or not. We have changed fine tuning the manufacturing, instead of 180-degree operation we go the 200 degrees operation. What is really going to change in that, and those kind of things are really required for this. And then we say that proposed design and process improvement, whatever we are suggesting, are really addressing all the faults within the flaws which we got in a system, or we are removing or mitigating completely or not. If it is not, then we need to again do a more analysis. If it is done, then good. So, what we say, we need to have a culture, we need to have a culture of continuous improvement. That is why this diagram is important, and when we go through the course, we will be keeping this in our mind. We understand and continuously improve in the way the product will function, or when we are trying to approach or we are trying to make any system, we should have this kind of a strategy, we should have a systematic analysis. Now, one more thing which I have written here, a warranty, something like that. Many times we require to do 100% tests in house, but we are not able to really simulate each and everything, all the faults in our own lab or our own company. That's why some companies started warranty period. Like now when they sell the product and they know that they already have achieved a 95% accuracy, and then they want to continuously improve. So they will give a warranty, and then they know the maybe when they are selling 100 products, there is a possibility 5 products will come back, and that will come back with a kind of the flaws and the kind of the faults which are there, and then they will improve. So that will also they will put back into the this loop. So they have a sold in the market, and they know it's a 95% reliability. 5% product may fail initial period. So instead of doing each and everything in house, or maybe doing everything in our own company, why not the customer do this kind of thing. Now what will happen in this case, the customer satisfaction also increases. We know that I bought a something and company is ready to change immediately. So I bought a one AC and now AC is not functioning well. I give a call back to the company, say, oh, there is a problem in my AC, please replace. And they found that failed AC, and then they can do this kind of again the feedback system, and then they improve. They find out whether design fault, whether material selection fault, or material fault, or installation something. So they do improvement on that. So that's why this policy helps a lot to the companies, and particularly for the startups. Now we'll now coming down to the final phase of this lecture, we say economic analysis of controlling surface degradation. We want to control the surface degradation, but is it really advisable? Will it really give a final thing? Yes, we should always continuously improve the surface or minimize the surface degradation. So we need to take a decision. That's why I say that whatever the surface degradation mitigation you do, there will be some sort of fund requirement. To allocate the fund, we need to take a decision, and taking decision without complete knowledge may not be correct. So that's why we say that to take a decision to allocate the fund for the to mitigate the surface degradation, we should take a logical approach, and that's what I am going to present in this slide. We say that whatever the protective measures you want to go ahead, there will be cost for that. So the value of the protective measure can be given by the left hand side. Now naturally we need to find out, if I am doing this kind of protective measure, how much saving is happening. So that's what is the cost saving or reduce material degradation, what is the really overall things, right. So what do we say, overall value, and then how much saving is happening and how much protective measure is costing to me. So that is where the difference comes. If this difference is negative, we should not upgrade, or we should not take any mitigation measures, or maybe some mitigation measure we should not be taken if this turn out to be negative. But if the saving is more than the measures which we are taking, actually we will be trying to take a decision. So this is a one simple thumb rule. However, we say that immediately we will not be able to know. Today I am taking some sort of protective measure, but I will know sometime maybe after 30 months or after 50 months or after 5 years or 10 years, something like that. So I should calculate all this value in the present value, right. So what will be the cost of the 10 after 10 years, I should account that. And then basically many times we say interest rate, or maybe say sometime we say what will be the return value. So that's what we are trying to say. Instead of this first this equation, we say equation 1, instead of that I will go for the equation 2. You see the present value of the protective measure, what is the present value, and then this present whatever will be the cost saving, and what will be present value of the protective measures. So whatever the measure, if I am taking annual measurement or annual sort of the maintenance, I should take a, and today I am taking a decision, so I should account all those things. So that's why this way in this value should be the cost and how much is the saving. And then we are using the word annuity in this case. What is the annuity? Annuity is a function of the number of years and return rate. How much I am expecting a returns per year? Is it the 10%, is it 15%, is it 20%? And as a number this rate of return increases, naturally we are getting a lesser and lesser annuity, and then saving whatever you say, if multiplication is lesser, quite possible the cost will be more than that, and then we will get a negative value, then we need to stop it. Now question comes, what is the really rate of return we are saying? is in this case I am assuming the 0.05, in this case 0.1, and in this case 0.15, and we are able to see annuity in this case 7.72. Naturally, this 7.2 say kind of a multiplication to the saving will be more compared to the 6.14, and that will be 6.14 will be more compared to 5.02. So, this is a what we go ahead, that what is the really expectation. If I say reliability of my company is the only expectation, I do not want money back, I do not want this, the name is a matter more, then maybe the R value will be much smaller. Well, that has been shown over in this figure also, that if value of R is continuously increasing, there will be some sort of mark over here. Beyond this, if my rate of returns is very high and then I am getting this value, I should not take any measure to avoid the surface degradation. So, there it will be unprofitable to control the material degradation or surface degradation. While in this case, if R value is low, in this case I can take measure, I can take measure, I can take measure. So, this is what comes. Now, question comes how we will go ahead with this. Every new business is a risky business, and whenever there is a risk involved, people will go with a number. Oh, high risk means we should get a fast money, otherwise there will be problem. Just to avoid that kind of practice, most of times high risk values project are generally the government provides a lot of support, and most of the time startup get support because of that. When they start up, they are coming with some new product, some new technology, some new process. Naturally, they require some support, and that's why the government provides support to them, that you don't worry about the rate of return that much. You do work, and maybe one day you will be able to provide maybe say remove all kind of surface degradation mechanism, or you will have a perfect surface and it will last for the 10 years, 15 years, 20 years. But at that time you take a support from a government, or maybe some sort of a partial support, or maybe say very small support, that is possible. And most of the institutions, they are providing also a lot of support for the as an incubation center, particularly for these reasons. Now, question comes, I am using the word saving. What is the meaning of saving? Again, it is a probabilistic. I do not know exact value. So, we say saving can be given in a probability of, if I do not take any measure, probability of the if I take a measures, and then what will be the if failure happens, if the whole system fails. So, 3 costs in this case, we say the cost of the failure, what will be the responsibility, and this is a probability of the failure if we do not take any precautionary measure or any preventive measure against surface degradation, and this is the probability where the surface degradation is accounted, and then we are trying to take some mitigation measures. So, this is what we go ahead. So, in this slide I am using the word probabilistic analysis, because we are talking about a saving and we are saying that this is a probabilistic. It is not the actual number, or maybe say it is not a deterministic number, and that has been shown. The probability of measures we are not taking at all, we are taking measures and cost. And this is what has been also clearly mentioned, the probability of the failure without preventive measures, probability of failure with the protective measures, and that is why it has been given, and here cost F is the given expense of the failing. Now, just to give a complete we say that knowledge about this is something like in here maybe say this is 0 here. We say the expense of the each failure of the cost is around 10,000, and then if likelihood, sorry, 1 lakh in this case, sorry, this is 1 lakh, okay. And then if likelihood of the failure will drop, if the initially if I do not go ahead with the protection, the probability of failure is 0.3, and then if I go ahead with all the measures, the probability of the failure drops to the 0.1. So, 0.3 minus 0.1 into the 1 lakh is the cost of the failure. When the failure happens, it will be costly that much. So, overall saving will turn out to be 20,000 in this case. Now, whether this probability is a continuous, whether the time dependent or not dependent, in the part time we are assuming it is not time dependent. So, we can go ahead with this, and that is where the saving has to come, and is again we are using the probabilistic and approach. So, it is not easy to calculate. That is why we say estimating rate of the material degradation is challenging. Reason being, because there is a little information available related to the kind of surface degradation, unless we have been doing a lot of work in that kind of product. That is why we say the feedback loop is very essential. We continuously do more and more, and we get more and more data, so that we are able to judge, we are able to give this kind of the mathematical model or probabilistic models. So, another one we say investment subjected to material degradation might decrease as the required rate of the returns rises. That is why the previous slide we showed one diagram. If R is continuously increasing, then finally judgment will come, do not do any mitigation of the degradation, let the component fail. We do not want that, and this is often the that is why the most of the companies do, they want the most of the returns at the beginning itself, or maybe initial years, and then they do not take a judgment, and maybe that is why the, as I mentioned, the government is trying to support those kind of industries, and the essential for them to survive and come up with a lot of good research work. Now, overall we required feedback loop, experience and knowledge. I am trying to promote my course. I say without knowledge you can't take a decision. So, you attend more and more lectures, more and more lecture, and more understanding, do more and more exercise to get this knowledge, so that you can take a decision in future without much problem. So, with this I say thank you for your attention.